In Lesson 8, we're going to start by talking about scientific notation. I'm going to talk about three things. I'm going to start by talking about powers of 10 and place value, which will lead us into the definition of scientific notation. I'm going to do some computations with scientific notation at the end of this part of the lesson. Steve's going to follow by talking about applications of scientific notation, and finally, at the end of this lesson, Candace is going to review some of the topics we've talked about over the last several lessons. So let's start by looking at powers of 10 and see how that relates to place value. We're just going to evaluate some powers of 10 to see if we see any patterns emerge. So I'm going to start by evaluating 10 to the 4th. Let's remember what 10 to the 4th means. That means we're looking at the product of 4 factors of 10. And what is that? 10 times 10 is 100, times 10 is 1,000, times 10 again is 10,000. How about 10 cubed? 10 cubed is 10 times 10 times 10. That's 1,000. 10 squared, 10 times 10, that's 100. 10 to the 1, well, that's just 10. 10 to the 0, well, that's defined to be 1. Now, before I continue, let's see if we see a pattern here. 10 to the 4th, that's 1 followed by 4 zeros. 10 cubed, 1 followed by 3 zeros. 10 squared, 1 followed by 2 zeros. 10 to the 1st, 1 followed by 1 zero. 10 to the 0, 1 followed by no zeros. So we certainly see a pattern when we're looking at positive or non-negative integer exponents on 10. Now let's look at the negative exponents. 10 to the negative 1, that is, by definition, 1 over 10 to the 1st power, which is 1/10, which as a decimal we write as 0.1. 10 to the negative 2, that's 1 over 10 squared, which is 1/100th, which as a decimal I can write as 0.01. Finally, 10 to the negative 3 is 1 over 10 cubed, which is 1/1000th, which we write as 0.001. So let's look at what's happening here. We have 10 to the negative 1. Our 1 is 1 unit to the right of the decimal point. When we have 10 to the negative 2, our 1 is 2 units to the right of the decimal point. We see the same pattern with 10 to the negative 3. What we're seeing here is a relationship between powers of 10 and place value. We have 10 cubed, we have a 1 in the thousandths place. 10 squared, we have a 1 in the hundreds place. 10 to the 1, our 1 is in the tens place. 10 to the 0, our 1 is in the ones place. Let's skip down to 10 to the negative 2. Here our 1 is in the hundredths place. So there's this relationship between the powers of 10 and place value. Let's look at that another way. Here we're asked to evaluate this rather long expression, but everything involves powers of 10, so the arithmetic should be fairly straightforward. So we have 3 times 10 squared plus 4 times 10 to the 1st plus 5 times 10 to the 0 plus 6 times 10 to the negative 1 plus 7 times 10 to the negative 2. This equals 3 times 10 squared, that's 3 times 100, or 300, plus 4 times 10, that's 40, plus 5 times 10 to the 0, that's just 5 times 1. 6 times 10 to the negative 1, we saw that 10 to the negative 1 is 1/10, so 6 times 1/10 is 6/10. And finally, 7 times 10 to the negative 2, that's 7 times 1/100th, which is 7/100ths. So adding this up, 300 plus 40, that's 340 plus 5, 345, and now we have our fractional part, 0.67. So here's another way of seeing how place value is related to powers of 10. That 3 times 10 squared gave us the 3 in the hundredths place. The 7 times 10 to the negative 2 gave us the 7 in the hundredths place. So this number, 345.67, we say is written in either standard form or decimal form. So now we're asked to use a calculator to evaluate some expressions in this table. We're using a calculator simply so that we can find patterns. Eventually, we should do these calculations without a calculator. So let's start by looking at the product of 1.3 times 10 to the 4th. So I'm going to pull out my calculator, and we reviewed how to find powers on a calculator in the last lesson. So I have 1.3, and I'm going to multiply that by 10 to the 4th power. So I'm going to take 10 and raise it to the 4th. That's 13,000. So I'm going to have my computer write in 13,000. The rest of the calculations, I'm just going to show you what I get using a calculator, and you may want to try these on your calculator at home to make sure you're getting the same number. So 4.57 times 10 cubed, my calculator tells me that's 4,570. 7.1 times 10 squared, my calculator tells me that's 710. 1.25 times 10 to the 1st, my calculator tells me that's 12.5. 9.5 times 10 to the 0, that's just 9.5. We should have known that. 10 to the 0 is just 1. 8.7 times 10 to the negative 1, 0.87. 3.2 times 10 to the negative 2, that's 0.032. And finally, 5.12 times 10 to the negative 3. When I calculated this on a calculator, I got 0.00512. Let's see if we see any patterns here. And what we're going to look for is where the decimal point occurs. When I have 1.3 and I multiply it by 10 to the 4th, where's the decimal point in this expression 13,000? Well, it's implied that the decimal point is here at the end of the number. So what's happened to the decimal point is the decimal point in 1.3 has moved 1, 2, 3, 4 units to the right. Let's see if the same thing has happened in the next row in our table. We started with a decimal point between the 4 and the 5, and when we multiplied 4.57 by 10 cubed, the decimal point ended up 1, 2, 3 places to the right. 10 cubed, the decimal point moved 3 places to the right. Does this pattern continue? If we multiply a number by a power of 10 with a positive integer exponent, is the decimal point in this case moving 2 units to the right? 7.1 times 10 squared, it worked. We got 710. 1.25 times 10 to the 1, did the decimal point move 1 place to the right? It did. How about 9.5 times 10 to the 0? Did the decimal point move 0 places to the right? It did. It didn't move at all. Now when we have negative exponents on our power of 10, what's happening to the decimal point? Well, 8.7 times 10 to the negative 1 gave us 0.87. Decimal point in this situation has moved to the left. Did that happen again here? 3.2 times 10 to the negative 2, decimal point moved 2 places to the left. Finally, 5.12 times 10 to the negative 3, the decimal point, which was between the 5 and the 1, moved 3 places to the left. So we see a pattern here which makes multiplying by powers of 10 very easy. So multiplying a number by a power of 10 with a positive integer exponent n moves the decimal point n places to the right. We also saw that multiplying a number by a power of 10 with a negative integer exponent minus m moves the decimal point m places to the left. Notice that in this description, m itself was a positive number. Now, some people say that the decimal point moves n digits to the right or left, and sometimes I even say n units to the right or left. N places, n digits, those both mean the same thing. These rules follow from the fact that place value in numbers is determined by powers of 10. That's why this arithmetic is so easy. So now let's formally define scientific notation. Now, scientific notation is commonly used to express very large and very small numbers. A number written in scientific notation is of the form a times 10 to the b, where this number a is some number between 1 and 10, but it can't equal 10, and b is an integer. This number a is sometimes called a mantissa. Now, this word may or may not be in your algebra book, but it does help to have a word to describe this first factor in scientific notation. So let's work a couple problems working with scientific notation. Now, before I start, we have this number 3.5 times 10 to the 12th power. Notice that we've regressed back to this symbol for multiplication, this little x symbol for multiplication, which we haven't been using in algebra. And this notation is often used in scientific notation, using the x for multiplication rather than a dot. So we just need to remember here when we're working that we're not seeing the letter x, but multiplication. So we have this example. Is 3.5 times 10 to the 12th a large or small number? Well, let's think about 10 to the 12th. That's a 1 with 12 zeros. That number's enormous, and we're multiplying it by 3.5. It is still enormous. So here's an example of a very large number, but in scientific notation, we don't have to write a lot of digits. So now we're being asked to let's write a lot of digits. Let's rewrite this number given in scientific notation in decimal notation. So I have 3.5 times 10 to the 12th. Okay, so I'm going to write down the digits in my mantissa, and then I have to think about moving that decimal point, which was here between the 3 and the 5, 12 units to the right. Let's hope I've left myself enough room. I pass by the 5, and I'm going to need 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's a big number. And sometimes it helps to group off the digits into threes to really get a picture of just how big that number is. Is 4 times 10 to the negative 8 a small or large number? Well, what does 10 to the negative 8 look like? Well, I have my decimal point, and 8 units to the right of that, I have a 1 with 7 zeros in between. That's a tiny number. And a tiny number multiplied by 4 is still pretty small. So let's take this number, 4 times 10 to the negative 8, and write it in decimal notation. So I have 4 times 10 to the negative 8. Well, I'm going to take my mantissa 4, and I need to move the decimal point 8 units to the left. Well, where is the decimal point? Well, there's an implied decimal point here to the right of 4, and I need to move that decimal point 8 units to the left. So I have past the 4, that's 1. I'm going to need 7 zeros. 1, 2, 3, 4, 5, 6, 7. There's my decimal point. And I just add 1 0 to the left of the decimal point for good measure so that you can see that decimal point. This is indeed a small number. So here's a big number. A $6 trillion debt is a big debt. Now, we have some expressions for some big numbers that we can write as powers of 10. For example, 10 cubed, that's 1,000. 10 to the 6th, that's 1,000,000. 10 to the 9th is 1 billion, and 10 to the 12th is 1 trillion. So when I see something multiplied by 10 to the 6, for example, I'm thinking in terms of millions. So what we have here is a $6 trillion debt. Let's write 6 trillion in scientific notation. Well, as a power of 10, a trillion is 10 to the 12th. So 6 trillion, we have 10 to the 12th, and we need 6 of those trillions. So we're just going to multiply it by 6. So 6 times 10 to the 12th, that's 6 trillion. So now we're going to go from decimal notation into scientific notation. Here, it helps to kind of visualize what's happening to the decimal point when we move this way. So we're starting with 2,500. Now, my mantissa is just going to be these digits 2, 5. Those 2 zeros are just indicating multiplication by powers of 10. So where's the decimal point going to go? Well, my mantissa is between 1 and 10. So I'm going to want to drop that decimal point in between the 2 and the 5. 2.5 is between 1 and 10. To get 2,500, I'm going to need to move that decimal point 3 units to the right. That's the same as multiplying by 10 cubed. So 2,500 is the same as 2.5 times 10 to the 3rd power. If I want to check, I can just take 2.5, move that decimal point 3 units to the right, make sure I get 2,500. So now let's write the small number 0.000205 in scientific notation. We're going to focus on the numbers that we're going to put into our mantissa, 205. We want our mantissa to be between 1 and 10. So the decimal point is going to need to go between the 2 and the 0 in those 3 highlighted numbers. Now to get this small number, I'm going to need to move that decimal point 1, 2, 3, 4 units to the left. That's the same as multiplying by 10 to the negative 4. So the number in standard notation, 0.000205, is equivalent to 2.05 times 10 to the negative 4. So what I have here is a table, and we're going to be converting from scientific notation into decimal notation and vice versa. In order to give ourselves some room to work, I'm going to just look at this table 1 row at a time. So focusing on the first row, I'm being given a number in decimal notation. I want to write it in scientific notation. So I'm going to focus on these digits 3, 5, 6. These digits will become the mantissa in scientific notation. And I'll need to put the decimal point between the 3 and the 5 in order to get a number between 1 and 10. Now I just have to do some counting. If I go from 3.56, but I want this number that was given in decimal notation, I'm going to have to move the decimal point 1, 2, 3, 4, 5, 6, 7 units to the left. So I'm going to multiply 3.56 times 10 to the negative 7. Now let me just say one last thing about this mantissa. These digits 3, 5, 6, which we used in our mantissa, these are called the significant digits in decimal notation. So the digits in the mantissa are the significant digits in our number given in decimal notation. Here's an example. We're starting with a number in scientific notation, and we want to write this in decimal notation. So I have 5.65, and I'm multiplying it by 10 to the 6, so I'm going to move that decimal point 6 units to the right. So I'm going to pass the 6 and the 5, and I need to go past 4 zeros. So have I moved 6 units to the right? 1, 2, 3, 4, 5, 6. I'm just checking my work here before I finish this example. So 5.65 times 10 to the 6, sometimes that's described as 5.6 million. We can see here that another way to say that number is as 5,650,000. Okay, we're starting with a very big number in decimal notation. We want to write it in scientific notation. our mantissa in this case is going to have 1, 2, 3, 4, 5 digits. I'm going to put the decimal place between the 4 and the 1, 2, 5, 4. What power of 10 do I need to multiply it by to get the original number? Well, the decimal point's going to move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 digits to the right. So my exponent on the power of 10 will be 11. Here we have 8.241 times 10 to the negative 5. Now when we have a negative exponent on our power of 10, we're looking at a relatively small number. When we rewrite this in decimal notation, we should see this. So I'm going to start by writing the digits in my mantissa, and I'm going to put them here kind of far to the right, because I know my decimal point is going to be moving to the left. The decimal point in the mantissa was here between the 8 and the 2, and I'm going to move that decimal point 5 units to the left, so I'm going to pass the 8, and I'm going to have to go by 4 zeros. So 1, 2, 3, 4, 5 digits to the left. There's my decimal point, an extra 0 in front of that for good measure, and I see that I have a pretty small number. Finally, I have a number 476 times 10 cubed. Now you're probably thinking, Anne, you've got this number in the wrong column. Isn't this scientific notation? Well, actually, it's not. 476 is not valid for the first factor in scientific notation. That first factor needs to be between 1 and 10. So I'm going to do some scratch work here in order to rewrite this in scientific notation. I'm going to write 476 times 10 cubed, and I'm going to focus on the 476. I can write 476 in scientific notation as 4.76 times 10 squared. And I still have a factor of 10 cubed. So this part, 4.76 times 10 squared, is just 476. And then multiplying 10 squared by 10 cubed, that gives me 10 to the 5th. So in scientific notation, what I have is 4.76 times 10 to the 5th. I'm going to finish off this part of the lesson just by doing some simple computations with scientific notation. The first thing we're asked to do is to double 1.4 times 10 to the 4th. So if I'm going to double that, I'm going to multiply 1.4 times 10 to the 4th by 2. Now the parentheses here are just for emphasis. I know that multiplication is associative, so really I could think about this as 2 times 1.4 times 10 to the 4th. A little bit confusing here. I've used a couple of different notations for multiplication, but that's because I'm just in the habit of using this multiplication symbol in scientific notation. The computation I'm doing, 2 times 1.4, that's just 2.8. So I'm left with the number 2.8 times 10 to the 4th. Now let's look at a product. We're asked to find the product of 2.5 times 10 to the 4th and 4.2 times 10 to the 9th. Just want to point out here that we're just looking at the product of 4 factors. We have the product of 2.5 and 4.2, and we have the product of 10 to the 4th and 10 to the 9th. I'm just using the commutative and associative properties of multiplication to rearrange the factors in this problem. So I'm going to do 2.5 times 4.2. I'm going to pull out a calculator for this. So 2.5 times 4.2, that's 10.5. My powers of 10, 10 to the 4th times 10 to the 9th is just 10 to the 13th power. Now, my result here isn't given in scientific notation, so I think I want to go just one more step so I can write my result in scientific notation as well. So I can rewrite 10.5 as 1.05 times 10 to the 1st power. Still multiplying that by 10 to the 13th power, So my result in scientific notation is 1.05 times 10 to the 14th power. Now let's find the quotient of two numbers given in scientific notation. So I have 2.016 times 10 to the 12th over 8.4 times 10 to the negative 9. So this quotient, 2.16 divided by 8 to the 4, I'll pull out my calculator to do that. And the power of 10, 10 to the 12th divided by 10 to the negative 9, that's 10 to the 21. So 2.016 divided by 8.4, that gives me 0.24. My result's not given in scientific notation, so I think I'll go one more step to rewrite it in scientific notation. So 0.24, that's the same as 2.4 times 10 to the negative 1. I still have a factor of 10 to the 21 in this problem. Adding the exponents on the two powers of 10, I end up with 2.4 times 10 to the 20th. Now in the next part of this lesson, Steve's going to show you how to enter numbers given in scientific notation into your calculator. So you could just pull out your calculator and have it compute this quotient. Steve will show you that in the next part of the lesson. One last example, we want to find the cube of 6.3 times 10 to the 15th. So I want to take 6.3 times 10 to the 15th and cube it. I'm going to be using rules of exponents here. Remember that if I have a product and I cube it, I'm going to be cubing each of the factors. So I need to cube 6.3, and I need to cube 10 to the 15th. So 6.3 cubed, 6.3 raised to the third power, that's 250.047. And I'm going to multiply that by 10 to the 45th power. So the mantissa of my first factor, I want to write this first factor in scientific notation, will be 2.50047 times 10 to the second power, all of that times 10 to the 45th. Let me remind you where I got the 10 to the second power. The decimal point here between the 2 and the 5 needs to move over 2 digits to get the 250.047. And finally, the last step's kind of straightforward. I'm just going to multiply those powers of 10, and that's the easy part of this problem. So now we're going to turn this over to Steve, who's going to work some applications using scientific notation.
Hello. In this part of the lesson, I'm going to work several application problems that involve scientific notation. One of the things that's really swell about scientific notation is it makes it easier to talk about science problems where really, really big numbers and really, really small numbers occur naturally in the problem. A couple of places this happens is astronomy, where you get really huge numbers, and chemistry, where you get little itty-bitty, teeny-tiny numbers. So I'm going to work some examples from astronomy and from chemistry. And in the process of working these examples, I'm going to talk some about using scientific notation on a calculator, and I'm also going to give you several examples of using proportions to help you imagine the unimaginable. And I think I'm going to establish that you can really have some fun with scientific notation.